Chapter 7, the quantum mechanical model of the atom. So quantum mechanics had its beginnings in the early 20th century. Before that, it was believed that all physical phenomena were deterministic, meaning that the forces acting on it right now absolutely determine its behavior in the future. But many famous physicists were doing experiments that revealed that subatomic particles, such as electrons, do not obey regular laws of physics. The present condition of those subatomic particles, those ultimately small things, does not determine the future condition. If you shoot an electron down a path and measure where it lands, and you do the same thing with another electron, it's not going to land in the same place. That's not how baseballs work. If you throw a baseball with exactly the same force and trajectory, it's going to go exactly the same place. If you do that with a baseball, it works. If you do it with an electron, it's almost guaranteed to go somewhere else. It doesn't follow the regular rules. The absolutely small or quantum world is where the electron lives. So these particles are so small that they don't obey the regular laws of physics. The large macroscopic world, things that we can see and feel, that obeys regular physics. What's really crazy about these absolutely small particles is that they can be in two or more different states at the same time. When they are observed, they have to be in one state or the other. So an electron can act as a wave, and it can act like a particle. It can be a particle and a wave at the same time. But when we observe it, we force it to be one or the other. Another way you can look at this, an unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. But when you observe it, you force it to be one or the other. And if that doesn't bother your mind, it should. It should be disturbing. So electrons are incredibly small. We've talked about them before, but just a nice analogy here. So a single speck of dust, we can see a speck of dust, but it's really, really tiny, right? Single speck of dust has more electrons in it than the number of people who have ever lived on Earth. Wow. Right? Electron behavior is important to learn about because electron behavior determines the behavior of atoms, and the behavior of atoms determines the behavior of the matter that we can see and feel. We can't directly observe electrons in atoms because they are too small to see, even with the most powerful electron microscope. But also the issue is that if you observe the electron, you change its behavior. So that's hard. Even shining a light on a beam of electrons changes its behavior. Yeah.
In an example, you have a question like what is the smallest particle? Is a photon or strong electron?
Well, the smallest of the main subatomic particles is the electron. Yeah. There actually are a lot of other particles. There's muons and gluons and Higgs bosons and all kinds of other particles. But we don't have to talk about those because we're chemistry, not physics. So, but all of those particles are in that ultimately small group, and they all behave very strangely. Okay, you may have heard of Schrodinger's cat. So we're going to watch a couple of cat videos here. And the point of this thought experiment about Schrodinger's cat is it demonstrates how taking the rules of quantum behavior and transferring it to the macroscopic world just doesn't work. Electrons behave in a very different way than larger real things like cats.
be. This wouldn't be a YouTube channel without a cat video, so without further ado, we present Schrodinger's Cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we will see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answered, please?
So that's from a great YouTube channel called Minute Physics, and they explain things in really kind of a fun way. Here's another one.
Hello and welcome to that have wiggled their way into popular culture. Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they'd react to various forces. Then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. So you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding science. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it when we go for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. Alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Anybody have any questions? Now, obviously, a cat can't be dead and alive at the same time. But that radioactive atom can be simultaneously releasing a particle and not releasing a particle. So this stuff, this quantum mechanics stuff, is disturbing, and it's very difficult to understand. And in actuality, no one really understands it. Some people understand it more than others, but nobody really understands. So just a couple of interesting quotations from scientists. Niels Bohr, who worked on this, said, "Anyone who is not shocked by quantum mechanics has not understood it." This is just, it doesn't seem right. Schrödinger of the Schrodinger's Cat experiment wrote, "I don't like it, and I'm sorry I ever had anything to do with it." Right? Sometimes when you're studying the universe, you find things that you don't like, that you wish you hadn't found, but you can't just say, "Oh, well, put that back, I don't want to know about that." It's there. And Albert Einstein, you've heard of him, he attempted unsuccessfully to disprove quantum mechanics until he died. So if Einstein can't disprove it, what hope do the rest of us have?
What do you think understanding quantum mechanics will allow us to do?
Well, understanding quantum mechanics has, quantum mechanics explains a lot of things. In fact, these are some of the things. So it explains the manner in which electrons exist and how they behave in atoms, and that affects all kinds of other things. Why are some elements metals and some are nonmetals? Why are some things very reactive and some things are completely unreactive? Why does aluminum lose 3 electrons to become a +3 atom, and sodium loses 1 to become a +1 ion? Why is that? Well, quantum mechanics explains all of that.
I know they're actually trying to use it without completely understanding it, because they're trying to make quantum computing and actually have it where it isn't in one state, like binary.
Yeah.
They're trying to figure out how they can get it to be in both states at the same time.
Yeah, so there's a lot of research being done, and we've learned a lot, and we can do a lot of things even though no one completely understands what it is. And so, if you're interested in physics, my nephew's getting a PhD in a form of particle physics, and he loves this stuff. He just eats it up. There's lots of math and crazy calculations and all kinds of crazy stuff. That's great. I'm glad he likes that. I took, 1 year of college physics, Newtonian physics, like that stuff. Like, I'm not going into physics because that gets really weird really fast, right? So we need different kinds of people because we're not all into the same things, and that's a good thing.